Today we're going to be talking about Newton's third law. But before we talk about Newton's third law, let's talk about his other two laws of motion first. So first off, we had the law of inertia, Newton's first law. For a body in motion tends to remain in motion, a body at rest tends to remain at rest unless acted upon by an outside force. So Newton's first law is really saying that objects have inertia, which is a resistance to changes in their motion. And when the net force is 0 newtons, so when the object's in equilibrium, they're going to move in a straight line at a constant speed. Newton's second law is net force is equal to mass times acceleration, F equals ma, or FMA. And it describes how forces affect an object's motion. So a net force causes an object to accelerate, and that's going to change how it's moving. It's going to change either how fast it's moving or which direction it's moving. When we talk about Newton's third law really defines force as an interaction between two objects. So let's talk more about that. So Newton's third law, as stated, is for every action there's an equal and opposite reaction. And this is not the best. Because here's the problem with it. It seems like it's saying that there's a cause and effect relationship, and that's what Newton's third law is. Like it's a list of events that happen. One action, then something reacts to it. And that's not what it's about. It's not, car drives past, dog barks. That's not Newton's third law. It's not one domino tips over and hits the other domino. That's not Newton's third law. It's not cause and effect. It's not a chain of events. A better way to state it would be to say that all forces are due to interactions between two objects, and each object feels a simultaneous force that's equal in magnitude and opposite in direction. So really, we want to be talking about an action force and a reaction force. And these action and reaction forces happen simultaneously. So as the action force is happening, the reaction force is also happening. Every force exists in what we call an action-reaction pair. So when we talk about an action-reaction pair, finding them is actually, it's not hard. So we gotta just figure out, if we write down what's going on as a sentence, we would take the subject of that sentence and the direct object of the sentence, and then switch the direction. So we switch subject and direct object, and then we switch the direction to the opposite way. So for instance, the horse pulls the cart east. Well, when we flip this around, the horse is now going to be the direct object. It's going to be what is being pulled. The cart is now going to be the one doing the pulling, and the direction will be west. Now this makes a lot of sense, right? If you imagine yourself pulling on something, that object pulls against you as well. So if you're pulling it forward, it pulls you backwards. So let's go ahead and try to identify the action-reaction pair for the following. So let's say for some reason I was walking down the street and Mike Tyson's there. And after being trained on the old school Nintendo, seeing Mike Tyson makes me think, gotta punch him. Now, if you ever are in the same room with Mike Tyson, please don't do this, because that is assault. But real quick, just write down what you believe the reaction for this action-reaction pair to be. Here's the correct answer. So, as my fist is pushing on Mike Tyson's face is going to push back on my fist. Action reaction. Now, that is not to say that Mike Tyson will himself have a reaction to my action and then go ahead and clobber me. There's a reason why I picked a notable puncher for this example. Um, and that is because, yes, if we were talking about cause and effect, and I was trying to trick you up there and say, hey, that's going to be the cause and effect, the reaction is really his face slowing down my hand as I'm punching him. So let's try another one, this time less violent. This is something we've all done before. When you walk, you push the ground backwards. The reaction force is the ground pushing you forwards. So if you ever notice when you, well, you should notice when you walk, you got to push backwards. If you're in track, your coach is probably going to tell you, you don't want to have, loud steps when you're running because that means you're hitting the ground and pushing it down instead of pushing it back. You really want to exert your force backwards instead of just stomping around on the track. Or if you've ever stood up in a canoe and walked in a canoe, you'll find that you're pushing the canoe backwards while it's pushing you forwards. And if you're trying to do this next to a dock, you'll notice that the whole canoe slides backwards relative to the dock. Let's try another one. A rocket pushes its fuel down. So for a rocket to work, it needs to have fuel and it pushes it the opposite way that it wants to go. What's the reaction for this? That's right, the fuel is going to push the rocket up. So until the rocket runs out of fuel, it's going to be able to go up. Now, we can also talk about Newton's third law as an equation. So if we wanted to write it like that, it would be the action force is equal to negative the reaction force. So equal and opposite. If a car hits a bug with a force of 10 newtons, then the car would feel a force of, well, in this case, I've labeled the forces F bug for the force on the bug and F car for the force on the car. So doing just switching stuff around then, I would get the force on the car is negative 10 newtons. Now, that doesn't seem right. How can the car get pushed because it's getting hit by a bug? Well, here's the thing. The force on the bug and the car are truly equal, but we can write it using Newton's second law as mass bug, acceleration bug is equal to the negative mass car times the acceleration of the car. So we just mod that. If we wrote it with their sizes relative to each other, the bug's going to have a tiny mass and a huge acceleration. The car, on the other hand, is going to have a massive mass and a teeny tiny acceleration. Yeah, when you hit a bug with your car feels a force, but it's not enough force for your car to appreciably accelerate. The acceleration is so tiny and over such a small period of time that you wouldn't notice it even if you were staring at your speedometer. But if you ran into a cloud of locusts and you hit 10,000 bugs, then you would notice. Or if you hit something bigger than a bug, you would definitely notice, right? When you're doing bumper cars, now they both have the same mass, and that same force affects their acceleration about the same. Now, let's try a problem like this. So let's say we had a cannon with a mass of 200 kilograms, and it fires a cannonball with a mass of 5 kilograms with a force of 400 newtons. What would be the acceleration in the cannonball? What would be the acceleration of the cannon? Then, just to wrap up, all forces exist in pairs. It doesn't matter what the force is. If it's some of the forces that we haven't talked about yet, like electromagnetism, two charged objects always attract each other. Or if we're talking about gravity, the moon is held in its orbit by the Earth's pull, but at the same time, that same amount of force acts on the Earth, and that's what causes the tides, right? So it's the moon's gravitational pull on the Earth that causes the water to slosh around the way that it does on Earth. So the magnitude of each force is always going to be the same. I can't push harder than I receive a push. If I punch a punching bag, the harder I punch it, the harder it punches me back. But since the objects can have very different masses, their motion can be very, very different. If I jump by exerting a force down on the earth, I push the earth away from me, it pushes me away from it. But since my mass is minuscule compared to the Earth's mass, even after quarantine, well, the Earth doesn't move a whole lot. It would be really bad if when I jumped up, everybody else on Earth went, "Whoa, what the heck was that?" But I would need a mass of nearly 10 to the 26 kilograms for anyone else to be able to notice. And then the direction of the forces are always going to be in opposite directions. So if I push something forward, it will push back on me. If I push it down, it will push up on me. So that's Newton's third law.